Okay, so 7.8 is over improper integrals. It's going to be our last section in this unit. And so basically dealing with an improper integral it's when you have an integral whose limits are either infinite or one of the limits is a vertical asymptote. That's basically it. So we're going to start with type 1 infinite integrals. Infinite intervals. And this is where you have a definite integral, and one of your limits of integration is infinity or negative infinity, or it could be both. All right, and I'm gonna kind of just draw out what they have on the next slide so that it's not all coming at you at once. So let's think of just the function 1 over x, which is a hyperbola, but I specifically want to think about this branch of it. I want to think about the branch in the first quadrant, which basically just looks like this when you graph it. And the x-axis is a horizontal asymptote. So let's say I want to evaluate the integral from 1 to infinity of 1 over x dx. So in terms of an area, I would be looking at that. And so you might think, well, there's a horizontal asymptote there, so the graph never meets the x-axis, so the area just keeps adding up, so it must be infinity, which is not necessarily true, right? We deal with adding up infinite quantities all the time in calculus, and they can add up to finite things. The whole idea of an integral, right? You're adding up an infinite number of infinitely thin rectangles, and that can add up to a finite value. So just because this is an asymptotic function doesn't necessarily mean that that area is infinite. The graph could be getting close to the x-axis fast enough that that area does what we call converges. And it just means it adds up to a finite value. And so here's kind of the way we're going to deal with it. Instead of infinity, I'm going to replace it with a variable. Let's say I did t. All right. Whoops. You know what? I just realized this isn't the function I want to be looking at. I want to be looking at 1 over x squared. Sorry about that. Because 1 over x actually does diverge, which we'll prove. All right, but 1 over x squared, this one does, the curve gets close to the x-axis fast enough that the area converges. All right, so if I were going to find the antiderivative of that, what is it in the chat? What's the antiderivative of 1 over x squared? Remember, you can rewrite it as x to the negative 2. Jill and Henry, you're about to be grounded. Out of there, Jill. Henry, close the door so I can't hear. Good. So it's negative 1 over x. And I'm going to do from 1 to t, right? So now when we apply the fundamental theorem of calculus, part 2, we plug in t, I get negative 1 over t. minus -1, which is going to end up being +1, right? All right. So now remember what we replaced, what t was. What we substituted t for was infinity. So now to finish evaluating this, I'm just going to let t approach infinity, which we know how to do from Calc 1. So what does 1 over t go to? What is that term going to approach as we let t approach infinity? Good. Yeah. Anytime we have a constant in the numerator and our denominator is getting infinitely large, that term's going to approach 0. So yep, that goes to 0. And I end up with 0 plus 1, which is just 1. Meaning for this curve, y equals 1 over x squared, the area underneath from 1 to infinity is 1. And that's basically going to be our approach to improper integrals with infinite limits, or on infinite intervals, is replace the infinite interval with a variable, evaluate the integral like you would normally, and then at the very end, let that variable approach infinity. Take the limit as that variable approaches infinity. And if you come up with a finite value, then we say that the integral converges. But sometimes you won't come up with a finite value. It will go off to infinity, in which case we say that the integral diverges or is divergent. All right, I'll give you a minute on this slide. You don't have to write down everything verbatim. You probably want to write down the definition of convergent and divergent. But this breaks down sort of the technique that you want to use if your upper limit is infinite, if your lower limit is infinite, or in case, the third case, you can have a situation where both limits are infinite. Then you want to split it into two separate integrals. And it doesn't matter where you split it. Split it at any constant. And then you just evaluate the sum of those two integrals. So you would evaluate each integral separately. But there are all types of functions that actually work out. There's a statistics has a very important function that's called the normal distribution. And it's actually a curve that is, you guys have, I'm sure, seen it before. It's a bell curve. And it's asymptotic in both directions. But it is convergent. The area under the curve is exactly 1. All right, so I'll give you a minute on this slide. Go ahead and give me a green check when you're done with it and ready to move on. All right, we're going to move forward. So you can see even with small differences, like the functions 1 over x squared and 1 over x have the same general behavior, but 1 over x squared, the curve gets close to the x-axis fast enough that that area converges to be a finite value. Whereas 1 over x, the curve also approaches the x-axis, but it does it in a fashion that's slow so that the area actually diverges towards infinity, meaning we just get more and more area no matter how far we go out. All right, what I want you to write down is what's in the blue box. It is true that the integral from 1 to infinity of 1 over x to the p will be convergent if p is greater than 1, but it will be divergent if p is less than or equal to 1. Again, just give me a green check when you're good with this slide. So we're going to look at sort of cover all cases of infinite limits. We're going to look at another example, but now where both the upper and lower limits are infinite. Okay, so what we want to do is just break this out into two separate integrals. And we do that just by choosing a constant to break it up at. It doesn't matter where you choose it, so you generally want to choose the constant to be whatever is going to be easiest for your calculations. So I'm going to choose 0 here. I'm going to go negative infinity to 0, 1 over 1 plus x squared, plus, and then we'll go 0 to infinity, 1 over 1 plus x squared dx. But I could have literally chosen any number. All right, and then we're going to rewrite our infinities using variables. So I'm going to go, all right, let's do the limit as a approaches negative infinity. God. Negative infinity, there we go. Of the integral from a to 0 of 1 over 1 plus x squared dx. Plus, and then I'll do b, the limit as b approaches positive infinity of the integral 0 to b 1 over 1 plus x squared dx. All right. Antiderivative time. This is one of our special antiderivatives that come in your table of integration techniques. Does anybody remember which one that is? Antiderivative 1 over 1 plus x squared. It's inverse tangent, yes. So that's what we get. We get limit as a approaches negative infinity of inverse tan x from a to 0 plus the limit as b goes to infinity of inverse tan x from 0 to b. Okay. Keep it up. The limit as a approaches infinity of inverse tan of 0 minus inverse tan of a plus the limit as b goes to infinity of inverse tan of b minus inverse tan of 0. All right, well, it would be helpful to know a little bit about what inverse tan looks like. So to give you some intuition for that, let's think about what tangent looks like. Now remember, all trig is periodic. So it repeats itself over and over again. But to have an inverse function, you need the function to be 1 to 1, right? Meaning it has to pass the horizontal line test. So to do that, we always have to restrict the domain of our trig functions. So for tangent, we actually restrict it to be between negative pi over 2 and positive pi over 2. And then tangent just looks like this, right? All right, so that's tangent x. So then inverse tangent is just going to reflect that over the line y equals x. And so basically what it's going to do is it's going to change the asymptotes to be from vertical asymptotes to be horizontal asymptotes. So this is pi over 2. This is negative pi over 2. Right? And there's the graph of inverse tangent. And that'll help us to kind of analyze what's going on with these limits, okay? Well, first of all, what's inverse tangent of 0? Yeah, good, 0, right? So both of these are, that's 0, and that's 0. All right, so what I actually have is, the limit as a approaches negative infinity of negative inverse tan a plus the limit as b approaches positive infinity of inverse tan of b. So now let's go to our graph of inverse tan again. And as we let our y values approach negative infinity, or our x values approach negative infinity, what do the y values of inverse tan approach? Yeah, does everybody see that? So I'll trace over it in blue again. As our x values approach negative infinity, our y values are approaching that asymptote of negative pi over 2. And so what I have here then is I have negative pi over 2 plus, all right, and as b approaches, as our x values approach positive infinity on inverse tangent, what are our y values approaching? That's it. So plus pi over 2. So then I have pi over 2 plus pi over 2, which is pi. So that integral, even though it's asymptotic in both directions, it does converge to pi. So I'll give you an idea of what that graph actually looks like. It's also kind of a bell curve. So that's what it looks like. And you can see it's asymptotic in both directions, but the total area underneath it is finite, and it actually converges to pi. Any questions on that? Is there an integrate function in Desmos? I started using, oh, look at that. Can I go from negative infinity? Oh! To infinity. One over 1 plus. I've started using this over GeoGebra just because I can do it in browser. EX. Oh, look at that. That's fun. But it doesn't shade it. I don't like that. I wish it would shade it. GeoGebra does. All right. Go ahead. Sure. Yeah, it's tough to wrap your head around, right? But you have to understand that we've been doing this for a while, right? Like the whole idea of taking an integral is adding up an infinite number of terms and still getting a finite value. So it's something we've worked with for a while, but it's like we're going to see this more too when we deal with sequences and series. But if I'm going to walk to the wall in front of me here, let's say it's 5 feet away, and I decide to do it in increments, I go halfway to the wall, so I've walked 2.5 feet, right? And then in the next step, I go half of the remaining distance. So the next step, I'm going to go only 1.25 feet. And then in the next step, I'm going to go half the remaining distance. Well, if I kept that pattern up, how many steps would it take me to get to the wall? Infinitely many. But that doesn't change the fact that where I'm first standing, the wall is a finite distance away from me, right? It's still only 5 feet away from me. But if I were going to add up all those incremental steps, I'd be adding up an infinite number of terms. But those terms would still add up to 5 feet in the end. So yeah, it is possible mathematically to add up a finite number of terms and get an infinite number of terms and get a finite value, which is all we're doing here. I know. Listen, the Greeks thought it was a paradox at first. They hated it. The famous guy named Zeno of Elea had written a book of paradoxes that calculus basically solved, but conceptually they're very difficult to think about. Like the Achilles and the tortoise, it's basically that same idea that I just went over, which would be like, it's the tortoise. Achilles is, super cocky, fast guy, and the tortoise is tired of his stuff, so he challenges him to a race. And Achilles says, fine, I'll murder you in this race. And the tortoise says, okay, well, give me a head start. And Achilles says, all right, any head start you want. And the tortoise says, okay, but before we start, I'm going to win this race and I'll prove it to you. And he goes, if you give me a head start, so here's the tortoise, and here's Achilles. I may be very slow, but I'm gonna be moved on to some point in front of you because you gave me a head start, right? And Achilles says yes. And he says, but I'll catch up to there. And the tortoise says, yes, but as you're running, no matter how fast you run to get to that first point, I'll have moved on some distance by the time you get there. Do you agree? And Achilles says yes. And he says, and then by the time you catch up to the second point, I'll still be consistently moving forward. So I'll have moved on to a third point in front of you. And so on, and the pattern continues. And so the tortoise concludes that Achilles can never catch him, because by the time he gets to the point that the tortoise will have moved on to some point in front of him. But so what that doesn't take into account, what Zeno didn't understand, was that you can have an infinite number of terms add up to a finite value. So even though it seems like it's going to take Achilles infinitely many increments to catch up to the tortoise, we can prove that if he's moving faster than the tortoise, yes, of course, he will catch up and pass the tortoise at some point in the race. So yeah, that's kind of the, listen, these ideas freaked a lot of people out. And there's a great BBC documentary for free on YouTube. It's called Dangerous Knowledge. And it's about the early mathematicians that were kind of dealing with these mental concepts, and a couple of them went insane. Go ahead, Tommy. Yeah. No. Well, 1 over x itself does go to 0. The area under the curve 1 over x from 1 to infinity does not. Right? Because remember, when we take the antiderivative of that, it's natural log x. And when you let natural log x approach infinity, it diverges. So yes, Tommy, you're just mixing up two things. 1 over x, the curve approaches 0. Right? The curve itself does approach 0. It's asymptotic. But the area under the curve from 1 to infinity does not. It's infinite. All right. So now we're going to talk about when you have a discontinuous integrand. Hold on. I want to look at. All right, we'll do this, and then we'll take a break, and then we'll do the comparison test. All right. And so this is a similar idea, but it's where one of your limits is going to be a vertical asymptote, right? So what that creates is a similar situation. Now we have our graph approaching a vertical asymptote. So we could have a scenario where it's approaching that vertical asymptote fast enough that the area converges, or a situation where it's not approaching the vertical asymptote fast enough, and thus there's infinite area and the area diverges. And we deal with it kind of the same way, except we're going to use one-sided limits. So for like a function like this, where the upper limit is a vertical asymptote, I'm going to replace that upper limit with a variable, say t, and then I'm going to take the limit as t approaches that vertical asymptote from the left-hand side. If that limit exists and is finite, then we have a convergent integral. If that limit is infinite, then we have a divergent integral. Okay? All right, so I'll give you the technique on this next slide. Just go ahead and give me a green check when you're good with that slide. So let's just do one of these examples. We're going to look at 1 over the square root of x minus 2 on the interval from 2 to 5. We can see from the denominator, right, since x cannot equal 2 because we'd be dividing by 0, we have a vertical asymptote at x equals 2, right? So that's where our infinite discontinuity is. So we want to replace that with a variable. Okay, so I'm going to rewrite this as integral from a to 5. The limit as a approaches 2 from the right. Okay, this is our left-hand limit, so we can only approach it from the right. And then I'll do 1 over root x minus 2 dx. All right, this is not just a trivial antiderivative. We don't just know it by looking at it. So what technique would you guys use to evaluate this integral? I think that's a good idea. And then du is just dx, right? And then we can do the integral of 1 over root u du, which is the integral of u to the negative 1/2 du, which is add 1 to that, and then divide by the new exponent. You would get 2u to the 1/2, or 2 root u. Okay, so that is, let's go back to my limit. Limit as a approaches 2 from the right of two root x minus 2 from a to 5. Plugging in 5, we get 2 root 5 minus 2 root a minus 2. And even though it's a one-sided limit, it's been a while since you guys have had to deal with limits, but we deal with one-sided limits the same as we deal with just overall limits, which is try a direct substitution. If that value doesn't break your function, that's your limit. So if I just plug 2 in for a, I get 2 root 0. Square root of 0 is still just 0, right? So my answer just comes out to basically 2 root 5 minus 2 root 0, which is just 2 root 5. So this integral is convergent, and it converges to 2 root 5. And so, Emma, if you want to think about this in a way, if it's bothering you that this is asymptotic, so the area never really totals up, that's why we use the term convergent, right? You're right, it's an infinite process, but what we're saying is that as we continue to add on area, our overall area is approaching a single value. In this case, that value is 2 root 5, right? It is an infinite process. We're going to be infinitely adding area, but that area will always be approaching a ceiling of 2 root 5. Whereas in a divergent situation, like this one, as we continue to add area, as we go out towards infinity, our overall area is diverging. It's just getting larger and larger. There's no ceiling on the total, right? Right. Okay. So let's just look at this graph in the calculator so we can. Oh, so yeah. Yeah, that's a good question. It should be 3. I'm sorry. I'm sorry, folks. You're right. This should be 3 because when I plug in 5 minus 2 is 3. And that's how I got the job teaching calculus. Knowing stuff like that in my interview. All right, that was a clerical error. This should be 2 root 3. All right, now let's look at that graph in the calculator. And so all we're saying is if we look at the area between 5 and 2, that vertical asymptote, the function approaches that vertical asymptote fast enough that the area converges and has that ceiling of 2 root 3. All right, that's a lot. I want to give you a general idea about the way the comparison test works. Let's say you're trying to prove that a function converges, and it's a really complicated function. What you can do is come up with another function. So let's say I want to prove that f of x between a and b converges, right? But f of x is really complicated, so it would be hard to find the antiderivative. If I can think of a function g of x that's always bigger than f of x, I'm not sharing anything. Damn it. Sorry about that. All right. Luckily, I didn't write anything too complicated down. I'm trying to prove that f of x converges on the interval from a to b. But it's really complicated, and I can't take the antiderivative of f of x. So if I can think of a simpler function, g of x, that's always bigger than f of x, and I can show that g of x converges on that interval, then it must be true that f of x also converges. The idea there being, on that interval from a to b, say that's a, that's b, if this is my function f, and integrating it is just the area underneath it, but it's too complicated for me to evaluate. But I did find this function g that's always bigger than f. So the y values are always greater than or equal to the fy values. And I show that that red area is finite. It has to be true that the blue area is finite as well then, right? Because the red area encompasses the blue area. Does that make sense? So if I prove that g of x converges, I've thus proven that f of x will converge by comparison. All right, so here's the comparison theorem in blue. Go ahead and write that down. Give me a green check when you finish writing down. What I just explained to you was basically part A. And once I get all the green checks, I'll explain how part B works. Basically the opposite or the inverse. And so we're just asked to show that e to the negative x squared is convergent on the interval from 0 to infinity. So they tell us which way to show it. I will tell you that this is non-elementary. So there actually is no way to find an algebraic antiderivative for that one. All right. So we're trying to prove that it's convergent, which means we want to think of a function that's simpler than this integrand, but bigger for all values on the interval 0 to infinity. Well, first, I'm going to have you, let's rewrite this as 1 over e to the positive x squared, because that's a little bit easier to look at. So what is a function? I want a function that's always bigger than that for positive values, right? For 0 to infinity. So the way you want to try and figure out what the comparative function is, it'll usually be related to the original. So in this case, I would go, okay, well, that's 1 over e to the x squared. What about 1 over e to the x? Is that always greater than or equal to 1 over e to the x squared? Well, if x is 1, they're the same, right? I'd have 1 over e and 1 over e. So, yeah. If x is 2, I got 1 over e squared and 1 over e to the 4th. Which one's bigger? Right. The one with the smaller denominator will always be larger, right? And so, yeah, we're going to say that this is true. This holds, right? So what I'll do then is just go, okay, let's look at the integral from 0 to infinity of just 1 over e to the x. All right, well I'll just do the limit as b approaches infinity of the integral from 0 to infinity of e to the negative x dx. We can take the antiderivative of e to the negative x pretty straightforward, right? It's just, I mean, you could technically do a u sub, but it's going to come out to negative e to the negative x. Oh, no, sorry, 0 to b, not 0 to infinity anymore. All right, well, let's look at the graph of negative e to the negative x so that we can kind of evaluate that limit. And so remember what I'm doing, I'm letting my input approach positive infinity, right? So when you look at this graph and my x values approach positive infinity, does it look like your y values are approaching something? 0, right? I mean, and we could also prove that by going, okay, well, this is the limit as b goes to infinity of negative 1 over e to the b plus 1. And so remember, what you have here is a constant over a denominator that's getting infinitely large. So that fraction is going to collapse towards 0, right? So that goes to 0. And then again, 0 plus 1 is 1. Just another example of how I got the job teaching calculus and statistics and all the higher level math. No big deal. All right. So we need to just make a concluding statement and say, I'll say, therefore, the integral from 0 to infinity of e to the negative x squared dx converges by the comparison theorem. And then we'll just smash it with a little dagger. Boom. Done.